So when we talk about pressure in fluids, what we mean is the pressure in both liquids and gases, because liquids and gases behave in the same way towards things like pressure and density. Although they are not the same thing, we know in terms of how the particles are spaced in liquids and gases that they are different, but for the purposes of our studies into pressure in fluids, into liquids and gases, we just kind of call them fluids because the particles in those are free to move. So there are quite a few factors that can determine what the pressure is in a fluid, whether it's a liquid or whether it's a gas. The first of those that we discussed was depth. We did a little experiment whereby we passed the pressure sensor downwards in a fluid, in a liquid, and found that the pressure was directly proportional to the depth. We call that H within our equation that we'll come to at the end of this little section. So pressure is directly proportional to H, which basically means that as depth increases, pressure increases with it. So you've got a constant gradient here, so direct proportion. The one thing that we did mention about that needs to be taken into account is the fact that air pressure actually decreases with altitude. So in order to get around that and make it hold for this term here and make it look the same as this, we choose our starting point for air pressure as the top of the atmosphere, and then we move down. Because we know that pressure does decrease. Remember, we looked at the hydrogen balloon that was rising, and it expands and expands as it goes further up because there are less air particles around pushing in on the balloon, so it's able to expand and then it will ultimately burst. Every balloon would burst like that. So pressure is directly proportional to depth. So as you go deeper in the sea, the pressure in the water increases. As we go upwards in the air, the pressure begins to decrease. So we've got a change in pressure as we alter the depth within a fluid, whether it's a liquid or a gas. The second quantity that we looked at was density. So density basically being your mass to volume ratio, having more particles there. So if there are more particles that are pushed down on you, if you're in a fluid, then you've got direct proportion there as well. So pressure is directly proportional also to density, which we indicate with the Greek symbol rho here. And a little example there is that salt water is more dense. You'll have heard of the Dead Sea, and you'll have seen people floating in the Dead Sea. It's more easy to float in the sea than it is in a swimming pool, for example, because there's salt in it. So there's more particles there. There's salt particles as well as the water particles, so it's more dense and therefore provides more pressure, so it's easier to float and harder to, I suppose, dive underneath the water. So we combine both of those statements, our direct proportion of P to H, which is depth, and our direct proportion of P to density, which is rho, and we put them into that term there. So pressure is directly proportional to density multiplied by depth. There therefore must also be a constant. The constant K we decided was gravity, it was G, the gravitational field strength, because that's always there. So that's really our third quantity that the pressure depends upon. So that gives us our equation for a pressure in a fluid, which is pressure equals rho GH, density times G times depth. So we use that then to go on and talk about, we'll just skip that, go on and talk about pressure and upthrust. So the whole idea of pressure increasing as you go deeper in a fluid is how we create something called upthrust. Upthrust is what you experience when you're in water and you feel that you are lighter. I showed you a Newton balance with some masses into a fluid, and you could see the reading on the Newton balance change, so that the apparent weight is less, some weight is lost, and that's due to a force that we call upthrust. And the first way that we looked at studying upthrust was via pressure difference. So if you've got an object like this suspended in a fluid or immersed in a fluid, then you've got a certain pressure on the bottom and a certain pressure on the top. Pressure will act all around this object, but we're only interested in what pressure is acting on the top and the bottom, because that's what's going to provide our upthrust. So because this surface here on the bottom is further down the fluid than the surface on the top, then it means that there is a pressure difference here, and it's that pressure difference that causes a difference in force and a resultant force in the upwards direction. So it comes from F equals PA. If we perform a calculation on, say, the pressure on the top, will be rho GH, where H will be the depth at the top is below the surface, and then we do a calculation for the pressure on the bottom with rho GH, where h will be the depth of the bottom surface from the top, we will find that there is a difference in pressure here. We can calculate from this equation here what the force is acting on both the top and bottom surfaces. If the force acting on the bottom surface is greater than the force acting on the top, then that means that there is going to be a resultant force, an unbalanced force that goes in the upwards direction. And that is what we end up calling upthrust. So I showed you an example of that, which kind of talks us through in more simple terms than you will get in an exam. You've got a tube suspended in water. Calculate the pressure on the top surface, calculate the pressure on the bottom surface. So you've got two different pressures there. The pressure on the bottom surface is bigger, you can see, than the pressure on the top surface. Your next step there is to calculate the force acting from just a rearrangement of your pressure equation. Force is equal to pressure times area. The area is the same for both the top and the bottom surfaces, so therefore because the pressure is bigger, you're going to have a bigger force over here. So you've got a difference in force there, which means you've got a resultant force in the upwards direction. If you just draw a simple free body diagram showing that they've got 29.4 newtons of force on the bottom versus 19.6 newtons of force on the top, your resultant force is in the upwards direction and it's 9.8 newtons.